Hello, everyone, and welcome to the HackFS workshop using drand and timelock encryption. Joining us today is Patrick McClurg, who will be taking us through this session. And with that, I'll pass it over to Patrick to get the session started.
Thank you very much, Rory. Yes, welcome everybody to the Drand HackFS workshop. First, we'll go over a little bit about the challenges, and then we'll dive into what Drand is and how it works. Then we'll finish up on what timelock encryption is and how you can use it. And then I'll field some Q&A at the end for any questions you might have along the way. So firstly, the challenges are twofold. First is for the best app built with timelock encryption. That might not make any sense to people who have not come across timelock encryption yet, but we will get to that very soon. Secondly, there's a prize for the best use of DRAND that solves an everyday problem and improves the security profile of a blockchain use case, a game, or improves the DRAND ecosystem. And there's $2,000 dues up for grabs for people who make the best apps, essentially. Okay, so what is DRAND? DRAND is a decentralized threshold network for providing publicly verifiable, unbiasable random numbers. It's based on threshold cryptography, as I said, and supports pairing operations, which we'll come to a little bit later. Essentially, when the network is created, a verifiable secret sharing process happens, and a shared private key amongst all the participants of the network is created, which no single party has access to. And then they emit randomness at epochs using the signatures from threshold cryptography scheme. It's built on BLS 12381. It's been tested, audited by Kudelski Security, and deployed at scale. The biggest user right now is Filecoin Network, who use the randomness from DRAND for leader election and some other proof of space-time related things. And currently DRAND randomness is available on the FVM, in the Cosmos ecosystem, and kind of on Ethereum. In fact, in one of the previous Ethereum hackathons, a team built Ethereum integration for DRAND called Derandomizer, which I've linked in the bottom of the slide here in case any of you want to try it for yourself. So a bit of a primer on how DRAND works. The notation is not super important. That's for the maths nerds who like all the extras. But in essence, DRAND emits randomness at epochs. Each of these epochs map to some time on the clock. So for our default network, that's every 30 seconds. Every 30 seconds, the nodes in the network gossip a partially signed message over the number of that epoch. And then when any node gains a threshold number of those signatures, they can aggregate them into one group signature that's valid for everybody in the network. Because, as I said before, no single node in the network ever has access to the private key, that signature is indistinguishable from randomness, as they can't pre-image it. Then we pass that signature through a hash function to remove some mathematical properties from it, and that becomes our random number. And this happens at every single epoch. Everyone in the network gossips all their partial signatures to one another and create the randomness. You might be familiar with some existing types of randomness, and I'll just give a brief breakdown of how DRAND differs from those. So the one most people are familiar with is dev random, built into all Unix machines and Linux machines and Mac machines. And there's kind of an analog in the Windows world. It's probably what you use to generate your Bitcoin private keys and to do lots of other day-to-day randomness operations. The biggest difference, obviously, is dev random is private randomness and DRAND's public randomness. So naturally, you wouldn't want to give your Bitcoin private key to anybody else unless you want them to take all your cash. DRAND, however, all the random numbers are public. Everybody can read them. Everybody gets the same random numbers. Additionally, you run random on your own device, but DRAND is a decentralized network. So there are lots of different participants working together to create this randomness. And finally, DRAND is verifiable. So if you were to get a number from a random generator, you've sort of got to trust in the fact that it's implemented correctly, that you're using the right generator, that the number that comes out is actually random. But because DRAND is based on a signature scheme, you can verify the fact that that has been generated correctly. And because of that property we mentioned before of not being able to pre-image the signatures, it's both random and verifiable, which seems counterintuitive at first. So dipping into some more of the public randomness world, for people who built on Ethereum before, they may be familiar with RandDAO. RandDAO is a DAO and a smart contract on the Ethereum network, where users commit to providing some bit of entropy to a smart contract, and at a later point reveal that entropy, and those bits of randomness are aggregated together into a final random number. How DRAND differentiates from this is, firstly, it's unbiasable. So you can imagine someone who has a lot of power in Ethereum network, like let's say a Coinbase, can actually take up many slots in this RandDAO contract, and they can choose to reveal or not reveal their little bit of that randomness based on the prior outputs. So if you manage to get some number of slots at the end of any RandDAO epoch, you can output, you can influence the final result. Also, a cool thing about DRAND being based on a signature scheme is that it's not just Web3 only. There's not a DRAND blockchain per se. It's not just on one blockchain. In fact, you can get DRAND beacons from any CDN. You can even get them from an adversary. And because they're verifiable, you can know that the DRAND network has generated that random number. A final project, which is very commonly used at the moment in blockchain ecosystems, is Chainlink VRF. Chainlink VRF allows you to request random numbers, and they create some proofs and write them somewhere before you use them to show that the randomness has been generated fairly. Firstly, like RandDAO, like the difference with RandDAO, Chainlink is primarily for on-chain applications, but also the trust model is very different. You're contacting one party Chainlink to run a function to output this random number, whereas DRAND, we have a network of participants, and you must trust that there's never a threshold number of malicious parties in the network. So the model is just a little bit different. So a little bit about the networking. We currently run two networks in production, the default network and the fastnet network. The core differences between them are that the default network emits randomness every 30 seconds, whereas the fastnet network releases randomness every 3 seconds. They have different URLs for interacting with them naturally. And also they run in slightly different modes. So in the default network, running in chained mode, each beacon contains a reference to the randomness from the beacon before it. This means that they form a bit of a Merkle DAG, and one drawback of that is that we can't do timelock encryption, which I'll come to later, using this chained mode. The fastnet network, by contrast, each beacon stands alone. It's not linked to the previous beacon through this chain of signatures. And that means that we can predict all the future messages, although not the signatures, for beacons that are going to come out in a fastnet. That's a secret sauce for timelock encryption, which we'll come back to in a bit. Also, a math nerd extra for any math nerds. In fastnet, we swap the G1, G2 groups in BLS in order to have smaller signatures and bigger public keys, because at foundation of the network, we create one public key, and at every epoch, we create a signature, which obviously is the randomness. So it means you can save gas costs if you're using it in the blockchain. So if you were to go into your terminal now and request some randomness from the DRAND API, you would come up with something a bit like this. The top entry here is the round number. So that is an epoch. That's a monotonically increasing number. Every time the network emits a piece of randomness is at a new round. It also maps a specific time on the clock. So you can predictably know when a specific round is going to become available. The next key in it is the randomness itself, which is a SHA-256 digest of the signature. The third field, the signature, is predictably the signature. It's a group signature for the entire network. So again, it's the key pair that was created during the distributed key generation process, and it's BLS12381. For chain networks, there's also a previous signature, which, like I said, links to all those previous beacons. So the easiest ways to get to Drand are to use the client libraries. We provided one in Go and one in TypeScript. Those are the official ones. Of course, you can get it through any CDN, through any HTTP client you wish, but these also bundle in verification of the signatures as well, just so you don't have to do it yourself. Also, everyone in our community seems to be a Rustation, so there are a whole bunch of different Rust clients for those of you who like writing things in Rust. And also, actually, this one, the top one, D, is also a CLI that can do time lock encryption and lots of other cool operations. So you should check it out because it's awesome. I've got a slide that says demo time now, which is slightly a lie. It's more a bit of a code walkthrough than a demo. Let me kill my presentation momentarily. I'm just going to go into the integration tests of the Drand client for JavaScript. I think it's an easiest way to understand exactly what's going on, and at least you can find it later in case you don't really remember what happened in that presentation. So we've got an integration test here. Essentially, you create some plumbing for fetching the public key of the network, which you can also do out of band. There are some other objects that allow you to not have to make requests for that. We provide three main functions. Firstly, you can fetch a beacon by the time. You can just pass in a classic JavaScript date, and the mapping between wall time and Drand epoch will be figured out magically for you. If you happen to know the epoch that you want to use, you can also pass that in and fetch a beacon just by its round number. Finally, we provide a watch function. So if you're, for instance, building a game that needs to consume Drand randomness in a timely fashion at every single epoch, you can get an async generator here that will call some callback whenever you receive the randomness. These are also more or less available in the same format in the Go library. So I shan't go into the Go library. But any questions on that, obviously, hit me up. And okay, so that was how to use Drand and a little primer on how it works. Let's now look into time lock encryption. It kind of does exactly what it says in the tin. It's encrypting something now that can't be decrypted until some future time has passed. The crux is that the Drand network is a bit like a reference clock. It ticks for every epoch and emits that piece of randomness. So we can rely on it to map clock time. Also, side note, my colleague has presented the time lock encryption scheme at Real World Crypto. So if you want to go a longer form explanation of how it works and all the gory details, you should definitely go watch the talk of an advanced encryption in Real World Crypto. So diving a little bit deeper, how does time lock encryption work? Well, it's simple. Fancy math, I guess, is the short term. For those of you whose eyes have just glazed over after going through school and discussing things like this, we're not going to dive into this. Don't worry, I've simplified it just a little bit further. So I said in one of the first slides that BLS12381 supports pairing operation. This is essentially exploiting some mathematical properties of the equation, as it were, in such that you can move different things around without changing it. So time lock encryption works a little bit like traditional asymmetric encryption. In traditional asymmetric encryption, you've got some public key that you use to encrypt a plain text, and the output is some ciphertext. And if you take the ciphertext and some secret key that has a relationship to the public key, you can combine them and decrypt the ciphertext and come out with a plain text. What time lock encryption does is basically turns the round number into a public key and the signature that gets emitted from that round number into a secret key. So like I said before, in unchained mode, because each beacon is not linked to the beacon before it, we can predict the exact message and the exact bytes that will be signed over by the network at some point in the future. That means we know that message now. We can use that as a public key to encrypt something. And we won't be able to decrypt it until the DRAND network emits that piece of randomness in the form of a signature at a later point in time. We've built some libraries around it, but also a cool web demo, which you're welcome to try now. It's called Time Vault. It is a web application for encrypting vulnerability reports so that when you find all those Adobe flaws, even if they take you out with an assassin, the world can still know what you found. It's built using Tlogjs. Obviously, it's backed by the DRAND network. I'm not going to demo it now, but you can obviously open it in your browser and give it a fiddle for yourself. All the code's open source. It's all on GitHub. And there's also a paper and ePrint if you want to know how it works. Before we do the Q&A, I will give the same, not quite a demo of Tlogjs. Again, we've got some integration tests in there. I think those kind of give the clearest picture of how to use this in practice. But essentially, we bundle some mainnet and testnet clients in here. There's a function called timelock encrypt. You pass a round number that you wish to encrypt to in there. There's some tooling as well around mapping that round number to a wall clock and back and forth. And then there's a timelock decrypt function, which takes also a client and takes your ciphertext. It supports an asymmetric encryption under the hood called AGE, actually good encryption, which works and looks a little bit like PGP. If you've already filled with Time Vault, you'll see that the output of a ciphertext here is this cool AGE encrypted file, which again looks a bit like a PGP ciphertext. So yeah, I implore you to get involved, check it out, and try out all the libraries. Luckily, I've left plenty of time for Q&A. So if anyone has any questions about DRAND or timelock encryption, I'm all ears. I see, oh, there are some in the chat here. Is linked to the generated random numbers set? Yes, indeed, it is a SHA-256 digest, so it's got a fixed length. Hypothetically, you could do your own hash key derivation function on top of the signature as well. There's in fact somebody raised a PR, somebody from the community raised a PR to do that on the DRAM repo. So there's some prior art there if you want to go and check out how they've done it, or come up with your own derivation function. Tony, is it going to be available on chain? That depends which chain you're using. It is available in the Cosmos ecosystem already through the Noise network. That's NOIS. Also, DRAND Randomness is included in every block header of the Filecoin network. So you can currently access it through the pre-Randau opcode if you're building an FVM actor, for instance. It's not currently available out of the box on Ethereum, although, as I said before, there's a project called RNGesus with a G and not a J that have built all those sort of relevant bindings to do on Ethereum if you'd like to do so yourself. Unfortunately, BLS operations are a little bit expensive, as currently there aren't pre-compiles on the EVM for that, but there is an EIP up for them, so you should go and, if you want them, go and hassle Ethereum people to get it merged. Max Ken asks, do you have a link to the PR for the transformation function to decrease the length? I can find one for you very quickly. Yes. So in fact, here's some useful links. You can find it somewhere here in the pull request. Let me pull it out for you. HKDF. Yes, here it is from Mr. Gorman. Although there also is some prior art in terms of, you know, if you, for instance, wanted to pick from one of 10 items, there's a cool project called Derandomizer with an S, the glorious British spelling and not the American spelling, which provide some tooling around doing that in the correct way to avoid modular bias and stuff. So worth checking that out. I haven't linked it here, but again, you can find all manner of projects under the Drand organization on GitHub. Surav asks, where can we find some use cases? I joined a little late, so I'm not sure it's been discussed. Well, that's up to you in the hackathon, of course. Some existing use cases we have seen, we've got some people building games on top of Drand. So for instance, for either randomizing item drops or defining the variables of certain NFTs for certain items in games. That's been one example. We're also working with a not-for-profit called Social Income, who are providing universal basic income in Sierra Leone. And they're working to use Drand to randomly select the people who should receive that universal basic income. We also developed a sample FVM map called Draffle, which is basically a bit of a raffle / lottery type app for drawing winners from a smart contract. Some other possible use cases to timelock encryption, a very cool one, which might be hard work in a hackathon, but MEV prevention, minor extractable value. If you could, for instance, timelock encrypt the mempool of a blockchain, you could stop miners from either reordering or not mining transactions based on gains they think they might get from them. Other use cases, generally drawing anything needs to be fair, lottery-wise, or in the timelock world, things like wallet recovery, automated deadman switches, auction applications. I'm sure there are plenty more that you guys can think up that I haven't thought of, and I hope that's the case. I'm excited to see what people build. How can we get your slides? That is a great question. I will make them available through the HackFS people. I'm not sure if there's a centralized channel for that. I can also stick them on IPFS after this and post the SID somewhere for people to retrieve them. Yes,
Patrick,
obviously, if you have any further questions, you can ping us on Twitter. We're also on Blue Sky because we're hipping with it. And there's a link to our Slack workspace here as well. Lots of people talking about different use cases and cool things that they're building in there. So feel free to get stuck in.
Hey, Patrick, yeah, for the slides, if you want to post them in the Discord channel, that might be another option as well.
That's the best idea, actually. Yeah, I will do that immediately after this talk.
Awesome.
Have we any final questions from the chat? Well, if that's the case, thank you very much, everyone. Thank you for listening. I hope to see lots of cool applications built on Drand. And any questions, find me, ping me, tag me, and hopefully I'll be able to answer them.
Oh, there was the last question.
Can you iterate on future file encryption? Well, one cool iteration on timelock encryption that we would love to have is some kind of proof system on top of it. Right now, there's no way to link. If I say I'm encrypting something now to prove that what's in there is actually what's been encrypted. That's quite a research project and would be a lot of work for a hackathon, but if somebody does it, that could well be worth a prize. But anyway, thank you very much and happy hacking.
Cheers. Thank you, Patrick. And thanks for everybody for attending. Good luck with the rest of the week hacking, and we'll see you for the next workshop in a little while. Cheers. Bye.